Hello everyone. Today we will be simulating quantum tunneling. But what is quantum tunneling? It is a property of quantum particles which allows them to pass through a potential energy barrier whose energy is more than the energy of the particle. You can definitely understand the reason why this mysterious tunneling is not permissible by classical mechanics. Think of it like a ramp connecting a lower level to a higher level. Obviously, a ball won't go up the ramp and reach the upper level if the kinetic energy of the ball is less than the gravitational potential energy required. But in the quantum world, stuff like this is very much possible. Why? Because in the quantum realm, particles' properties are explained by waves. A particle's position or velocity and other stuff are all wavy and uncertain. And this strange wave is governed by the absolutely goated one and only Schrodinger Equation. This equation is basically a wave equation with the square root of -1 for some reason.
Hell no, man.
The solution of this partial differential equation is the infamous wave function psi, which is a complex number. So we can calculate its modulus squared, which turns out to be the probability density or the probability per unit length. So upon integrating it from say A to B, we'll give the probability of finding the quantum particle between A and B. This is called Born's statistical interpretation. The game plan is we shall make a quantum particle strike a potential step or barrier. To do that, we need to first solve the time-independent Schrodinger equation for a free particle. The reduction of the time-independent Schrodinger equation from the original time-dependent Schrodinger equation can be done only when the potential energy function is time-independent. A free particle is obviously free, which is why I wrote Vx is equal to 0. We see that the wave function is a plane wave given by a general solution a e to the power ikx plus b e to the power minus ikx, where k squared, which is the wave number squared, is given by 2me over h bar squared. This is an equation of a general plane wave. To obey Born's statistical interpretation, the wave functions must represent probability densities. And the rule which probabilities must obey is that they should add up to be equal to 1. Let's see if that holds in this case. Well, that just can't happen, right? That's why we say that a plane wave is not normalisable. Instead, what we do is that we take a superposition of many such plane waves and get a physically accepted wave function which is known as the wave packet. Taking the combining coefficient ak to be a Gaussian function, we get something called the Gaussian wave packet. Upon evaluating the integration and imposing the condition of normalization, this is what it looks like. Here, sigma indicates the standard deviation, which is the measurement of the spread of the wave packet. Now you can easily show that the total probability will be unity. If I plot this function in Desmos, you can visualize the wave function. The red graph and the purple graph indicate the real and imaginary parts of the wave function. On increasing the standard deviation s, the wave widens. I can compute the probability density by squaring and adding the real and imaginary parts of the wave functions. And upon integrating it in all space, we will get 1 as expected. Isn't it beautiful? Since our simulation involves potential energy steps or barriers, which the quantum particle will try to cross, we will compute the energy of the particle and compare it with the height of the barriers. As we are dealing with non-relativistic quantum mechanics, the energy of a free particle is given by E equals p square over 2m, which is essentially the kinetic energy. From the de Broglie relation P equals h bar k, where k is the wave number, plugging it into the energy formula, we get h bar squared k squared over 2m. But wait, this only works for plane waves. As our wave packet is composed of many momentum components, it has a spread or uncertainty in energy. To calculate the expectation value of energy, we need to operate the wave function with the momentum operator, which is given by minus IH bar ddx, Note that this is basically an eigenvalue equation. On evaluating p cap psi, we operate it with p cap or minus I h bar ddx once again to get p cap squared psi. We know that the Hamiltonian operator h cap is given by p cap squared by 2m plus v, but here v equal to 0 because we are dealing with a free particle. Upon plugging this in the expression for p cap psi, we get this big equation with 4 terms. Now the expectation value of Hamiltonian is given by... Yeah, whatever. This is the expectation value of energy. Till now, we have got two things. One is the wave function we got at time t equals 0 by solving the time-independent Schrodinger equation, which is the Gaussian wave packet. And the other is the expression for the average energy of the particle, which we would calculate in the program just for comparing it with the potential height. Otherwise, it does not have a direct connection with the program's algorithm. As usual, we would first import all the necessary Python libraries or modules required for the program. Those include NumPy and matplotlib. Also, dark theme is a must. The main idea is we would plug in the wave function at time t equals 0 and let Python solve the time-dependent Schrodinger equation to calculate its time evolution. Upon studying from this amazing book on computational physics by Abhijit Kargupta, I got to know this. The general approach for numerically solving PDEs is to implement the finite difference method. Speaking in simple words, as I do not want to make this video math heavy, in the method of finite differences, we shall break up the xy plane into a network of discrete points. You might think of it to be like a grid. If the number of points allotted to the x-axis is capital N, we shall define the step potential energy in a Python function and return an array which is 0 in the first half of n and v0 from half of n onwards. For the case of potential barrier, the returned array will be 0 everywhere except from n1 to n2, where it will be v0 or v0. Obviously, both n1 and n2 are integers. Next, we shall define the Gaussian wave packet, which is the wave function at time t equals 0, in another Python function. Here, I have first initialized a 2D NumPy array whose 2 rows indicate the real and imaginary parts, while the columns indicate the value at each discrete space point. It was at that moment I realized that Python can handle complex numbers. So I defined a one-dimensional complex array, psi, in block letters, stored the real and imaginary parts of the wave function together, and returned it. As I told you before, the xy plane is broken into several discrete points on an imaginary grid. So the x and y coordinates on that grid can be represented as an ordered pair of integers xi, yj, where I and j are indices. The same type of discretization will hold even if one of the variables is time. We will divide time into discrete timestamps. For a multivariable function, psi of x, t, we can apply the Taylor series expansion and use the discretization method to arrive at the following. We discretize the time derivative in backward difference method and the space derivative in the central difference method. As we have already guessed, we plug them into the time-dependent Schrodinger equation. After a quick calculation, we arrive at this result. The time evolution of a wave function can be written in a matrix equation. Psi of t plus 1 is equal to A inverse b psi t, where A and b are the matrices shown. Small letters a and b are equal to I dt by 2h bar and I h bar dt over 4m dx whole squared, respectively. This numerical method for solving PDEs is known as the Crank-Nicolson method. As you have already guessed, I will use Python functions extensively in this code, as it is a good coding practice and keeps the workflow clutter-free. We make a function named TDSE, which stands for time-dependent Schrodinger equation. Firstly, we define the constants small a and b. Then with the proper use of NumPy's diag function, we created the matrices capital A and capital B. Matrix C is the final time evolution matrix, which is given by A inverse B. After that, we define the time evolution array, small letter psi. It is a two-dimensional complex array whose rows denote space points, while the columns denote their corresponding time points. We initialize this array at 0th timestamp with the Gaussian wave packet. You know the reason why. Since our Crank-Nicolson formula was an iterative relation, we start a for loop iterating over the timestamps, inside of which we simply write the formula. Then we calculate the probability density at each time step by squaring the absolute value. Then I returned both the wave function and probability density together in a list. The next Python function is for plotting an animation. I will go through this superficially as this part is very methodical and straightforward. First, I have asked the user if he or she wants to see only the probability density or the wave function along with it. Since probability densities are what matters and putting the real and imaginary parts of the wave function makes the graph messier, I have kept the option of hiding them. I have plotted the arrays including the potential step or barrier, set the title and axis labels, wrote the update function for animation, and finally the option for saving the animation. A small interruption. Actually, the saving process of the animation can be only done if you have the software FFmpeg installed in your device. If you don't have it installed, then you can watch my previous video, which was on the topic of central force motion, which I simulated and animated. There I have briefly explained the procedure of installing the software FFmpeg. You can find that video in the playlist, in my playlist on computational physics, whose link I will definitely attach in the description. The last and final Python function is the main function. Here I have written a menu-driven style message and asked the user to select either of the two options for step or barrier potential. I have provided a set of default parameters for each case, which the user has the option to select. If not, the user will be asked to input their own set of parameters. After the user inputs are complete, I have defined the x domain and the space step dx using NumPy's linspace function from the number of points. Then I have initialized the potential energy function depending on the choice of the user, followed by x0, which indicates the initial position of the Gaussian wave packet, which is q orders of sigma away from the middle, where sigma is the standard deviation of the wave packet. The wave number is calculated using 2 pi over L, where L is the wavelength. The average energy is also calculated using the formula which we painfully derived, and I have printed it along with the height of the potential barrier for comparison. Next, I have stored the wave function solution and the probability density by invoking the TDSE function. And fed those into the animation function. At the very end, I have called the main function, so Python executes it first, and the rest will follow along. Okay, so I have started the CMD or command prompt from that particular directory which contains the Python file. The name of the directory is Qt, which stands for quantum tunneling. And to run that particular Python file, what I need to type is this particular command, that is Python, and after writing Python, I would just simply type in the name of the .py file. I don't even have to type the entire name. I can just press tab and the name will be shown automatically. Now to start the program, I will just press enter in 3, 2, 1. Let's go. So this is the menu driven message. On top you can see it's written quantum particle simulation. After that there is a welcome message. Welcome. This program will let you visualize the time evolution of a quantum particle as it passes through a step potential or a potential barrier. Now there are two options. Press S for step potential, press B for potential barrier. So we can start with step potential first. So let us type in capital S and press enter. So here I get a default set of parameters. I will quickly go through each one of them because you are already familiar with them. So first, starting with the mass of the particle, which is set to be equal to 1. Same goes for the case of the reduced Planck's constant h bar because we are using natural units. Followed by capital N, which is the number of space points, which has been chosen to be 1000. V0 is the height of the potential barrier. L is equal to 20, which is the de Broglie wavelength in space units. Why space units? Because we are using a different set of units. We are not using units like meters or something like that. Since the entire space is divided into 1000 points, so in that particular sense, we are going to define other units of length, such as the de Broglie wavelength or the sigma, which is the standard deviation, like that. Okay, so sigma is equal to 40. What is Q? Q is the initial position distance. So the initial position of the wave packet will be situated at 5 orders of sigma before the start of the potential barrier. And from where the potential barrier will start, it will start from half of capital N. So if there are 1000 points, so the potential barrier will start from half of that, that is the 500th point. Or I should say the potential step will start because we have chosen the case for step potential. So anyways, dt is the time step, which is the time increment, you can say, and number of time points is 100,000. So as we are just starting off, I think it's a good choice to select the default set of parameters. So let's type y and we get a message. The average expectation value of energy of incoming particle is equal to 0.049 and the height of the potential barrier is 0.03. So the average energy of the incoming particle is more than the height of the potential barrier. We will get to the understanding of that later. And here is also a message written that time dependent Schrodinger equation is being solved. Please wait for a few minutes. And it will take some time because there are 100,000 time points. The loop will actually be executed 100,000 times, which will take a few minutes. So let's wait for that.
A few moments later.
Yes, so it says the Schrodinger equation is solved and there is a question, do you want to only plot the probability densities? So as I told you before, plotting all three of them together, those are the imaginary and real parts of the wave function and the probability density together, will make it messy. It will make the plot a little bit messy, but we will still plot the three of them because this is the first time we are executing the program. So do you want to only plot the probability densities? No. Next question, do you want to save the animation in your current working directory? Yes, we can save it. So Y, select the iteration increment, for example 500. I prefer large increments for quick saving. I can choose 400, no problem with that. FPS, 30 FPS. I don't want to waste my memory by selecting higher FPS values. And this will take some time because Python is actually rendering the video for us. So it says animation saved successfully with the file name quantum_tunneling.mp4, and in another window you can see the beautiful animation of the time evolution of the particle. As it is given in the legend above, the magenta colored curve indicates the probability density. As you can see, the probability density on the right side of the barrier is more than the left side. That is because the height of the potential barrier is less than the average energy of the particle. So the probability of the particle penetrating the barrier is more than the probability of reflection. You will find this animation saved as an MP4 file in the current working directory. Now we shall run the Python file once again. We will choose step potential again, and this time I will run the program with my own set of parameters. So no. Okay, the first parameter which I have to enter is the mass of the particle. I have also included the examples in brackets for quick reference. So the mass of the particle is 1. Enter the value of the reduced Planck's constant, that is also 1. Enter the number of space points, that is again 1000. Enter the number of time steps, that is once again 100,000. Enter the height of the potential step or barrier. Now here I will change it to be equal to 0.05. Enter the de Broglie wavelength of the particle in space units, that is 20, and standard deviation is 40 as usual. Then the distance, that is the q value, which is 5, that's the default one. Now time step is again 0.03, and yes, so I only change the height of the potential step or barrier. As you can already guess that this is the case when the height of the potential barrier is more than the average energy of the particle. You can see the average energy of the particle is 0.049 and the height of the potential barrier is a little more than that, that is 0.05. Now let's wait while Python solves the time dependent Schrodinger equation for us.
2000 years later.
And Python has solved it. Do you want to only plot the probability densities? Now let's do that. Now I don't want to make the plot messy and I only want to see the probability densities, so yes. Do you want to save the animation in your current working directory? Yes, we can save it. Now the iteration increment 500 is okay. FPS is 30 and it's saving. Let's wait for some time. It says animation saved successfully with file name quantumtunneling.mp4, and here is the animation. Okay, so let it start once again so we can see it. Yes, it's starting. It strikes the barrier and I can see some non-zero probability on the other side of the barrier as well, even though the height of the barrier is more than the energy of the particle. Now that can be an example of quantum tunneling. Even though when we talk about quantum tunneling, we generally refer to the potential barrier, not the step potential. We will see that in a moment. But still, this is also very, very interesting to watch. Also, one thing to note here, even though you can see a non-zero probability density on the other side of the step potential, the transmission probability is 0. It can be mathematically shown that the probability of finding the particle on the other side exponentially decreases with distance and the particle is ultimately reflected back. Now if I plot it again, yes, this time we will go for the barrier potential, that is the potential barrier. So we press B, capital B, and as again we are doing it for the first time, I think it's better to go for the default parameters, right? So yes, now you can see the average energy of the incoming particle is 0.049 and the height of the potential barrier is 0.03. So the potential barrier is of a lesser height than the incoming particle, so I can expect the particle to actually penetrate the barrier easily and go to the other side. So let's see what happens.
One eternity later.
Yes, the Schrodinger equation is solved. Do you want to only plot the probability densities? No, we will plot all three of them. Do you want to save the animation? Yes, we want to. Select the iteration increment. Let's select 450. Let's select something different this time. FPS is 30 and it's saving. So let's see. After saving is complete, this is the animation we get. As expected, a larger amplitude of the probability density is being transmitted to the other side of the barrier, while a very little is reflected. This looks so nice, isn't it? Okay, now we will again choose the potential barrier, but this time I will input my own set of parameters. So, enter the mass of the particle. Guess what? I will type 0.2. Let's see what happens. Just wait for it, okay?
Okay.
Enter the value of reduced Planck's constant, that is 1. Enter the number of space points, that is 2000. It will increase the resolution. Enter the number of time steps, again 100,000. The ending position of the barrier is 1015. So at the 1015 space point, the barrier will end and it will start, you know where, it will start at exactly at the middle. So if there are 2000 space points, it will start at 1000, which means it is a very thin barrier. Enter the height of the potential barrier. Height of the potential barrier is 0.03 as given in the example. The de Broglie wavelength is 70.944. Okay, just stay with me. The standard deviation is 40. The distance of initial position is 5. The time step 0.03. Now, as you can see, the average energy of the incoming particle is 0.02, while the height of the potential barrier is 0.03. So now, this is the case when we will witness quantum tunneling, as the height of the potential barrier is less than the energy of the particle striking it. So let's see what happens. Here is the animation which got rendered. As you can see clearly, there is a non-zero probability of finding the particle on the other side of the barrier, even though the barrier's potential energy is more than the average energy of the particle. The potential barrier is very thin, from 1000 to 1015 space point, so basically 15 space points wide. Choosing a thin potential barrier helps in increasing the tunneling probability, which is given by this expression. This, my friends, is tunneling, a bizarre quantum phenomenon. I have rendered 2 more animations which I would really like to show. This one has a potential height of 0.5, which is greater than the particle's energy, which is 0.44. You can see that the particle is bouncing back after striking the barrier. This is happening because I have drastically decreased the de Broglie wavelength to 15. Decreasing the wavelength results in less wave behavior and more particle behavior. In fact, quantum mechanics reduces to classical mechanics in the limit of lambda tending to 0. So the particle is behaving much like a classical particle, like a tennis ball, and bounces back from the barrier as it does not have sufficient energy to surpass it. There is negligible penetration. The other one is similar to the previous one, with the difference being the potential height, which is less than the particle's energy. This causes the particle to pass straight through the barrier almost without any reflection. This also indicates classical behavior when the bombarding particle has more energy to surpass the barrier. It is as if the barrier isn't even there. So that's all for this video. I tried to make this video a bit different from my other videos, by including memes and GIFs. If you want me to make a video on some specific topic, or if you think that I need improvement in some aspect of presenting the concepts or explaining the ideas, then please write me in the comment section, because your opinion matters a lot. I will end this video with a slideshow of all the animations which I have rendered. So sit back and enjoy. This is Physics with Shoham, signing off. We'll see you again in the next video.